All right, now let's look at a problem we have seen many times in Calculus 1, optimization problem, right? So let's read the problem first carefully to see if we can formulate it as a optimization problem for multivariable function. So now we're going to make a rectangular box. So usually we draw a diagram over here. So we have a rectangular box, okay, without a lid. So this top is empty, and we want to make this one with 12 surface area. So we have surface area is 12 square meters of cardboard, okay? Find the maximum volume of such a box. So we want to find out what is the width and what is the length and what is the depth. Okay, so x, y, z, we can do that. So we want to find the maximum value of the volume. So we want to maximize the volume. Now, how do we do that? We actually going to design a function. So we're going to look at the volume function. So the volume is x times y times z, right? We can call this function f of x, y, z is equal to x, y, z times that. And we know x must be bigger than or equal to 0, in fact, bigger than 0. Y bigger than 0, and z being bigger than 0. Otherwise, we won't be able to do anything, right? So now, what do? We want to find the maximum value of this, but there is a condition over here. Otherwise, we're going to use just as much material as we want. The condition is that the surface area must be 12 square meters, right? And then we're going to find the surface area. The bottom, okay, we have x times y. And we have 4 sides, right? 4 sides. And we have 2yz and 2xz, right? 2yz and 2xz, right? These 4 sides. So we have 5 sides, but not 6. Okay. So together we have xy plus 2yz plus 2xz is going to be equal to 12. Okay. So this is a condition. Now, when the equations are not so complicated, the function isn't complicated, we can solve this condition and put it back. So we solve z, and we are familiar with xy, right? So z is going to be equal to, we can factor z out, xy plus 2y plus 2x z is equal to 12. So z is going to be equal to 12 minus xy over 2y plus 2x, right? And we put it back, so 12 minus xy over 2x plus 2y. That would be the same thing. So our fxyz now actually is a function of f of xy. Let me call this function v of xy. Anyway, it's a volume, right? And then we have xy times, here we have z is 12 minus xy over 2x plus 2y, right? That's the one. Okay. And in fact, we can factor 2 out because that's not going to be too important. So, but let's keep this. So this one over here is going to be 1/2 x plus y, and on the top we are going to have 12xy and minus x squared y squared. And then we are going to find its maximum value. All right, now it's time to take 2 partial derivatives. Let's be very careful because when we have a complex looking function, it's very easy to make algebraic errors. So we need to be very vigilant. Let's look at the first derivative with respect to x. And then we have 1/2 is a constant, so we can leave it over here. And we're going to use the quotient rule. So it's x plus y squared. Remember, we are taking the derivative with respect to x. So look at the numerator. We have 12y. Derivative of x squared is negative 2x over here. And y squared is unchanged. And then we multiply it by the denominator, which is x plus y, right? And then subtract the derivative of the denominator is 1, so that's easy. And then we have over here, be sure to put a pair of parentheses over here, xy minus x squared y squared, right? Okay, now we can try to simplify. This is 1 over 12, and then we will have over here, we have x plus y squared. And then when we put it back, we need to use FOIL method also to expand it. So we have 12xy and minus 2x squared y squared. That finishes the first term over there. And then plus 12y squared and minus 2xy cubed. And then let's remove the pair of parentheses, negative xy and plus x squared y squared. So now let's try to simplify. We are going to have negative 12xy, positive xy cancel. And then we will have negative 2xy squared and positive x squared y squared, actually they are combined. And then just let's make one more step, and this is going to be 1/2, and denominator is going to be x plus y squared. We need to be extremely careful, look back to see if we have done anything wrong. I think we are fine. And then we will have 12y squared minus 2x y cubed, and then we have minus x squared y squared, right? So let's try to erase a little bit over here, and then we're going to go over here, and then we can also factor y squared out. So we have y squared over 2, and then we have x plus y squared, and then we have 12 minus 2xy and minus x squared, and that's the one. And by symmetry, we can confidently write down, because x and y, they are completely symmetric, we have x squared over 2 times x plus y squared, and then here we're going to have 12 minus 2xy and minus y squared. And then we let fx, fy equal to 0. We know x cannot be 0 and y cannot be 0. So we have denominator x plus y, they must be positive as well. So in fact, we know x bigger than 0, y bigger than 0, right? So we have over here a pair of equations, 12 minus 2xy minus y squared is equal to 0, and 12 minus 2xy minus x squared is equal to 0. So from here, we also look at some kind of substitution, but we can see 1 subtract 2, then we have something like this. We have x squared minus y squared is equal to 0. And that means x minus y, x plus y is equal to 0. We know both of them are positive, so x minus y is 0, and x is equal to y. So now what? We put it back. So now we have 12 minus 2x minus x squared is equal to 0. And that means 12 minus 2x squared minus x squared is going to be 0. And that's really nice because we have 12 minus 3x squared is equal to 0. And we have 4 minus x squared is equal to 0. And x is equal to 2. If x is equal to 2, y is also equal to 2, right? All right, at this moment, we basically know what should be the dimensions of this box and to get the maximum volume. But on the other hand, let's try something that our textbook doesn't try to do. Let's try to see if this point over here is going to be actually our local maximum. Because we only have found one critical value, it has to be the global maximum as well. So let's look at second order derivatives. I know it's going to be a pain, but let's try to be very careful and try to do the job over here. So let's try to find fyy. Okay, fyy. That's the second order derivative over there. But x squared over 2 is a constant, so we can factor this out. And we're going to use, instead of quotient rule, we're going to use product rule to find the derivative over there. So derivative of the numerator with respect to y, we're going to have negative 2x, right, and negative 2y, right, and then multiplied x plus y to the negative 3, no, negative 2. Okay, not yet. And then we have plus numerator, we have 12 minus 2xy minus y squared. And then we have a derivative of negative 2 x plus y to the negative 3, which is not too bad. Okay. Now, once we have this one, we can plug in the value, right? We can say x is 2 and y is 2. But the good thing is that this term over here must be 0 because we solved the equation to get this. So you only need to plug in the first term over here. So this is going to be x is 2, so we have 4 over 2, right? And then we have negative 4, negative 4. So we're going to have negative 8 over here. And then this one over here, we're going to have 2 plus 2 is 4. So it's 4 squared, right? And that's what we have. So we will have 2 over here. And then we have negative 8 over 16, and we have exactly negative 1. So the value actually is pretty easy, and we can be sure that fxx at this point at 2, 2 is also going to be negative 1. So now we just need to find another second order derivative. And then we have a product rule over here to apply, and this is what we're going to have. So take the derivative of the first factor, we're going to have just x, right? Okay, and then times the second factor, we have 12 minus 2xy and minus y squared over x plus y squared, right? And then we're going to take the derivative of the second term. The first term is just x squared over 2, right? When we take the second part over there, we're going to actually using again the product rule instead of the quotient rule. So we have a smaller degree for x plus y. So we have 12 minus 2xy minus y squared. Take the derivative with respect to x. And that means we're going to have exactly negative 2y left. And then we have x plus y to the negative 2. All right, and then we keep this term, 12 minus 2xy minus y squared. And then the derivative of x plus y to the negative 2 is negative 2 x plus y to the negative 3. Okay, and then we plug in x is 2 and y is 2, right? And we know that this will be 0. And we also know this is going to be 0. So again, we only need to do the middle part. So at x is equal to 2, y is equal to 2, fy of x is going to be equal to 4/2, and then -4 is from over here, and then we again have 4 squared, and that's going to be 2 times -4/16, and we see this time we have -1/2. Okay, and there is no doubt that now we're going to be able to find D. D is fxx times fyy minus fyx squared, and that's going to be -1 squared minus -1/2 squared, and that's 1 minus 1/4 and 3/4. That's positive. So we have fxx is negative and D is positive. So 2, 2 is a local maximum. And since from the context it is clear that since this is only 1, since it is the only critical value, we know it is also the, sometimes the global, sometimes we say absolute maximum, maximum. And we can also find Z. When x is equal to 2, y is equal to 2, we know Z is going to be equal to, we have the formula back over here is going to be 1. All right, Z is going to be equal to 1. Okay, I think that's all we want to have, and then we're going to have the volume over here is equal to x times y times z. That's going to be 4 cubic meters. That ends our computation for this second example.